Hello and welcome to this demonstration in the course for Secure Systems Engineering. So, we will be looking at a demonstration of how PLT works. PLT is essentially used to achieve a position independent code for functions. It is used quite a bit in order to achieve address space layout randomization, and as we have seen in the previous lectures, ASLR can actually prevent a lot of attacks. So, this particular demonstration would actually show how would we create a PLT code, or rather how PLT code actually works internally. So, the code that we use over here is present in the virtual machine that is shipped that comes along with this course, and this code in particular is present in this directory NPTEL-codes module 5 PLT. So, we use two C codes over here. One is mylib.c and driver.c. So, mylib.c compiles to a library libmylib.so, and driver.c uses this library and creates the executable called driver. So, mylib.c looks something like this. It is essentially a library for a doubly linked list. It defines a structure for the list which is defined in mylib.h. This is a doubly linked list, so it has the data and it has the previous and the next node pointers. And there are a lot of functionalities which are present in the in this code. So, for example, you could add a new node to this list, you can delete a node, and you can actually print all the elements in the list. So, this particular code is called from driver.c as follows. So, this is an example over here. You see that we have included mylib.h, and we have a main function over here. We initialize the doubly linked list, create nodes like this, new node. So, we have created 3 nodes N1, N2 and N3, each comprising of the data A, B and C, and then printed the doubly linked list. So, in order to compile the mylib, we run the make file. So, we run make clean and then make, and what we see is that we are able to create a library libmylib.so. Similarly, we could also make the driver as follows. Okay. So, there is a warning which is present here which you can ignore, but the important thing for us to consider is that we are linking the driver.c to the library using this -l mylib. The output is driver. So, when we run driver as follows, to get it to run, we need to first set the LD library path, that's set as follows. Make it point to the current directory and run it, and what it prints are the nodes in the doubly linked list comprising of A, B and C. Okay. So, let us look at the disassembly of the driver code. So, this can be obtained in the file driver.dis, and we will see it over here, and we will go to the main function. So, this is what how the main function looks like in assembly code. Now, we compared this with the actual main function written in C, and what we see is that the various function calls to the library like init, new node, print, delete and so on are all invoked over here through the call function. However, what we see over here is that the compiler has actually modified it slightly, and instead of calling new node directly, it calls something like new node at PLT. So, let us see what actually happens in this new node at PLT. So, you could refer to the previous lecture also to see what this PLT actually means. So, let us use GDB to run driver, and we would break at. So, we run driver. Okay. So, let us see. Okay, so we open the driver.c code, find out the address, find out the line where new node is called, that is line number 19, and we put a breakpoint at line number 19 like this, and run the code using R. And what we see is that there is the breakpoint at line number 19. So, let us disassemble the code here. So, we see that we are at the call to new node at PLT, and this new node at PLT is present at the location 8048530. So, this corresponds to a PLT section in the code. So, we can single step through that and see that we are now in the new node at PLT. We can disassemble this and see that it comprises of 3 instructions: an indirect jump, a push, and a jump instruction. So, during the first call of a new node, which is at this call, so this first jump works as follows. It essentially jumps to the address which is specified in this location over here, that is the location 804A024. So, let us see the contents of this location 0x804A024, and we see that it contains 080485536. So, what it means is that this jump would jump to the address 080485536. Now, in the first invocation of new node, which is at line number 19, what we notice is that this address is in fact the next line in the PLT, or the next instruction in the PLT. So, essentially what happens is that during the execution, this jump essentially jumps to the next line in the PLT code. Then here there is a push instruction, a push 0x30, and a jump to this location 0x80484C0. This location would be in the loader, which essentially resolves the actual address of new node, and the resolver would then fill in this location over here with the real or the correct address of new node. So, let us see this happening. So, we will single step through this, see that we are in the next line, single step again, and see that we are at the jump. Now, we are going to jump into the resolver, which is here, and we can come out of this resolver by entering command finish, and we see that we have come out of the resolver. So, what the resolver has done, it has gone into this particular address. So, this is the got entry for new node, and it has filled in the correct address for new node in this location. So, let us verify that. So, we can rerun this same command as follows, and what we see is that this value present in this location has changed to F7FD165F. So, if what we see is that this address is in fact the address of new node. So, printing the address of new node, we see that there is a match. So, essentially what is happening is that during the first invocation of new node, it jumps into the PLT and then obtains an offset from the got entry for that particular function new node, and then goes into a resolver. The resolver resolves this address of this function and modifies the got entry over here as we see in this thing, and then continues the execution. Now, during the second invocation of new node, we would directly jump using this indirect jump to this location, that is the location of new node itself, and therefore only the first invocation of new node would actually require the resolver to be used in order to resolve the actual address of the new node function. All subsequent invocations of new node would directly jump to the new node function using this indirect jump, and we can continue execution. Now, what we see here is that there is a malicious function. Now, what we can do is we can actually trick this entire thing into executing this malicious function. Note that the main function we see over here, there is no invocation of malicious function, but what we will show is that we can trick this entire system into invoking the malicious function. Let us see this as follows. So, let us restart the GDB, and we will put a breakpoint in line number 19, breakpoint at line number 19, and also a breakpoint in line number 20, and then run the program. And this single step instruction, and as before we have gone into the new node PLT. Now, what we will do is note down the address of the got entry. So, we would see that the got entry as before is at the location here. Okay, this is all that we require. We will continue executing, and what we see as done before, that this particular got entry would be filled with the actual address of new node. We can verify that again as x/x and p/x ampersand new node. So, you see that as before, the resolver has actually resolved new node during the first invocation. Now, what we can do is we could modify the got entry, and we could make it point to the malicious function as follows. So, what we do is set int got entry is this. So, it is already in my clipboard, equal to ampersand main. And what we see is that the got entry has been modified and now points to the malicious function. Now, in the second invocation of new node, it goes into this PLT and picks and jumps to the address as specified in this location, which essentially is the malicious function, and therefore it is going to execute the malicious function. Let us see, if we continue execution, what would happen. So, right enough, instead of executing new node, it has indeed come into the malicious function. So, in this way, what we have seen is that we've seen how GDB can be used to actually change the execution pattern of this particular program. In a more malicious application, in malware for example, an attacker would use a vulnerability in the program to modify the GOT entry and thereby change its execution pattern. So, we will be putting up a few assignments or some challenges on the website, and you could actually try to use the vulnerability to show how you could use the GOT entry to modify the execution pattern. Thank you.